Frankenstein, and this year I'm honored to be serving as the president of the USC Citizens for Land Stewardship. First, I'd like to thank the Upper St. Clair Community Foundation and especially the Quest for Lifelong Learning Subcommittee for providing our community this wonderful educational opportunity. I think it's a really good thing we're doing, and we appreciate it. And CLS is pleased and excited to sponsor this Quest course, and I would like to take a moment to thank Preston and Annette Scheimer, who did all the hard work to coordinate this program. We thank you very much. Brought home to us why this is so important by describing water availability legitimately as water everywhere and just one drop to drink. Then Ruth Ann Omer talked to us about water management as part of our community infrastructure. Ruth Ann stressed the importance of balance, balance, balance as we strive to manage our water in its various forms: stormwater, sewage water, and our natural surface waters. Last week, Tom Page taught us about how to determine when a natural stream system is compromised, and he explained to us an emerging technology, natural stream channel design, to restore stream channel and bank stability. All of the information that we gain from these courses supports Ruth Ann's reiterated theme of balance, balance, balance. Our course today furthers that theme because our course today describes our local, active water quality monitoring program. The knowledge and understanding gained from this program will help us as we strive to balance, balance, balance all of the issues intrinsic to sustainable community development. Now, wrong button. Okay. Many of you who know us in CLS know that our CLS board members wear many hats. One of the other prominent CLS roles I play is as the captain of our local CVMP stream teams. Today, my colleague Bob Ramey and I are going to talk to you about the work of our CLS CVM stream teams. Bob formerly worked for Carnegie Mellon University and is currently an active volunteer with the CLS CVM stream teams. Also important to today's presentation is stream team number 3, because later this afternoon we'll join stream team number 3 streamside at the Claire's Kennel monitoring site right outside the building here. And you'll be able to watch the stream team in action as they execute an actual water monitoring session. There we go. The USC Citizens for Land Stewardship Water Quality Monitoring Program is made possible with funding and technical support from the PA Department of Environmental Protection through the PA DEP's Citizens Volunteer Monitoring Program. Some members of the DEP came here and gave us some training. They've provided all of the materials for our program, so we couldn't do it without them, and we do thank them. Water pollution is divided into 2 primary categories. Point source pollution, which is pollution from defined sources. You often hear this referred to as end-of-pipe pollution. This is generally waters that have been used in an industrial or commercial process and then are cleaned up and returned to a receiving surface water receiving body. This kind of pollution is heavily regulated at both the state and the federal level. A second major division of water pollution is called non-point source pollution. This is pollution from diffuse sources, and it's delivered to surface water primarily, and to groundwater for that matter, primarily by runoff after snow or rain. This would include fertilizers, herbicides, insecticides, oil and grease, road salts, sediment, and bacteria. The DEP CVMP program, which we're a part of, is focused on non-point source pollution. The goal of the program is to enhance understanding at the local and state level of water quality and water quality issues. The CLS CVMP Water Quality Monitoring Program is volunteer powered. 14 local volunteers make up our 4 CLS stream teams. The CLS stream teams support the CVMP goal by executing water monitoring activities at 4 points within the McLaughlin Run watershed. This is a map of the Chartiers Creek watershed. Let me let me get a pointer here so I can point some things out to you. This roughly oval dark black line is the boundaries of the Chartiers Creek watershed. All of the streams, which primarily everything you see on here is streams, some of these straight gray lines are roads, but predominantly this is all streams. Within this strong black line, all of the streams flow towards Chartiers Creek. Outside of this dark black line, all of the streams flow away from Chartiers Creek or into another receiving body of water. That's what we learned is defined as a watershed, right? Okay, and this heavy black line that flows approximately down the middle is the major stream in the watershed, and it's Chartiers Creek. And Chartiers Creek flows into the Ohio, whoops, sorry about that. Chartiers Creek at the end of its run flows into the Ohio River. Our watershed, the McLaughlin Run watershed, is a sub-watershed of the Chartiers Creek watershed. Now this isn't a physical boundary for Upper St. Clair, I just wanted to give you an idea of where we are on the map. And the two streams you see on here that are the two primary streams in the McLaughlin Run watershed, certainly not the only two streams, but the two primary streams. The bottom stream is McLaughlin Run stream, which flows into Chartiers Creek, and the largest tributary to McLaughlin Run is locally referred to as Grazier's Run, and that's this stream here. And our stream teams monitor at 4 sites within this watershed. Stream team number 1 does water quality monitoring on the McLaughlin Run stream, and they execute this at Drake Loop. That's the old park and ride parking lot down by Kings. We park right in that parking lot and do our water sampling on McLaughlin Run there. Stream team number 2 monitors on Grazier's Run, and we do that at what I've referred to as the power plant. Bob Ramey has explained to me that that's a misnomer. That's actually a, help me Bob? A substation. But forgive the misnomer, the power plant is used over and over in the presentation. You'll just have to live with me on that. Stream team number 3 monitors on McLaughlin Run right out back here by Claire's Kennels. That's where we'll be monitoring today. And stream team number 4 monitors on McLaughlin Run at the very edge of the golf course. Actually, we park in the tennis court parking lots and do our monitoring. We walk just into the golf course property. Throughout the presentation today, you'll see these same colors over and over again. This light orange, light green, dark orange, and actually this, I'm sorry, should be a dark green. You'll see those 4 colors over and over again in the data charts to represent the data from the various monitoring sites. Last thing I'd like to say about this is it's interesting, and we hope to see some significance to this as the data is collected over time. The fact that we're doing some monitoring immediately upstream of the natural stream channel design and immediately downstream of the natural stream channel design that you walked with Tom last week. So we're wondering if over time we'll see some implications in the water quality data. And at this point, I'm going to turn this over to Bob Ramey, who is an active member of our stream team number 3, volunteer water quality monitoring team, and he's going to talk to you about some of our water quality monitoring results.
Here's an overview of some of the field parameters. The field parameter basically is something you measure in the field as opposed to sending it to a laboratory to have it done. We measure air temperature, water temperature, pH, conductivity, dissolved oxygen, and discharge. We'll talk about pH, conductivity, and dissolved oxygen a little bit later. Air temperature and water temperature, the reason we take that, if it turns out there's a significant difference between the two, it could imply that there's some thermal pollution involved. In other words, if you're out there and the water temperature is 90 and it's only 60 in the air temperature, something's happening and you want to know about it. We track that. Discharge is computed rather interestingly. We measure the width of the stream at several different places and the depth at 5 different points across that place. And then we put ping pong balls in the stream and time how long it takes to go, say, 10 meters. The cross-section gives you an idea of the volume flow, and the ping pong ball's timing tells you how fast it's moving. So we come up with a cubic meters per second discharge rate. So much for that. There are also laboratory parameters. We take water samples. We fix them with nitric acid or sulfuric acid to stabilize the sample, pack it in ice, and it gets shipped off to Harrisburg. It has to be done in about 24 hours in order for the samples to remain intact. And Harrisburg then does a laboratory analysis on all of these particular components. We'll talk about these in detail on the next couple of slides. Now, one of the things that we measure in the field is pH. That's how acid it is. It's the water is 7. To give you an idea of what pH is, for some other things, battery acid is 0.5, vinegar is 2.9, urine is 5.9, human blood is about 7.3, baking soda is 8.3, and ammonia is 11.2. So sulfuric acid is very acidic, and ammonia is very, very basic. Specific conductivity is just that. It's actually 1 over the resistance. So basically the resistance is measured, and then its reciprocal of that is taken, and that's usually measured in something called microohms or microsiemens. It's directly related to the total dissolved solids. That's primarily related to the geology of the area, the stuff that comes off the land naturally, but runoff in this area contributes greatly to conductivity in terms of particularly calcium chloride that's put on the road. And we'll look at that data in a few minutes. The conductivity is related to temperature. It's related to the mobility of the specific ions that we're talking about, whether they're have a valence of 2 or a valence of 1. But it does not tell you what specific ions are there. We do not do an analysis specifically for calcium or specifically for chloride. Now, the dissolved oxygen is one of the more complicated field tests we do. It's a 4-step process. We carefully collect the sample by, and we'll see that when we go out in the field, by immersing a small bottle under the water, facing upstream, being careful not to let air bubbles get into it, obviously, because you're measuring dissolved oxygen. And once that's done, it's mixed with 2 specific chemicals which produce a precipitate. This is typical of a lot of field tests. You typically produce a precipitate, and then you dissolve it, and then you titrate it. You don't go out in the field with volumetric flasks and calibrated pipettes. You have eyedroppers, and you count drops, and this is one of those kinds of tests. You want to emphasize this is dissolved oxygen. It's not organically or inorganically bound oxygen. It's actually the oxygen that's dissolved in the water that the fish can breathe. It gets there by 2 or 3 different ways. Simply with thermal equilibrium of the surface area, or if it's going over rapids, it gets aerated, or in the case of a lot of plant life underneath, through photosynthesis. Now, the alkalinity and the total suspended solids are done at Harrisburg, but basically the alkalinity is very important to the water because low acidity is very bad for aquatic life, and the calcium carbonate buffering system pushes the pH up, and it provides a way for additional acid basically to be neutralized before it affects the pH. And it's determined, this system around here is primarily in the form of carbonate and bicarbonate. In the human body, there's a similar buffering system. It's a combination of carbonate, bicarbonate, and phosphate. It's seen in a lot of biological systems, this buffering capacity to maintain a pH which is relevant to the so-called homeostasis of the system. Total suspended solids, TSS, suspended, not dissolved. These solids include inorganic material like clay and silt, and organic material, bacteria, plankton, detritus, solids. Now, some solids that can be dissolved, like iron, for example, it can be dissolved, but if the pH goes up, it can start to precipitate out. So there are both, iron can be either a not dissolved or dissolved contribution to TSS. The way that's measured, there are 2 or 3 ways of measuring that. One is with a turbidity. It's a turbidity test. Basically, you take a defined sample and in a chamber, and you put a collimated beam of light on it at about, I think the color temperature is about 3,000 Kelvin. And then you measure it at right angles with that, the scattering of the light. That gives you turbidity. We don't do that. It's too hard to get an equivalent milligrams per liter figure out of that. Another way that's done, and the way Harrisburg does it, they have a very fine glass filter. They take a defined amount of, basically shake the bottle up, pour a known volume through this glass filter, which has been weighed ahead of time, and you dry the filter, and then you weigh it again. The difference is that's the solids you've collected. So that's typically the way that's done. In deep water, they have a very interesting way to do it. There's a little, I've probably never seen one, but it's a disc about half a foot in diameter, and it's quartered black and white. It's lowered down into the water on a chain with a graduation on it. And when you can't see it anymore, you read off on the chain how deep it is, and that's a measure of the turbidity for deep water. We don't do that either because our water's about that deep. Okay. Now this is some of the data, and we have Jan to thank for this. She's been collecting this for over a year, put it into an Excel chart, and then made this display for us. So and that's a lot of work, and not only keeping it up to date, but just getting it so it looks presentable. I'm impressed. pH, the healthy range for pH is roughly in the range 6 to 9. If you get above that or below that, aquatic life suffers. Now there are some animals like brook trout and yellow perch that can go down to 4.5, but that's a toleration level, not really a survival level. As we said before, human blood is about 7.3, and most mammals tend to live in that area. Cold water fish tend to be like a little bit lower. So these sort of tell the tale. Now these are tests that we do here. We do the pH here. The alkalinity is done in Harrisburg, and the healthy range for alkalinity is measured in milligrams per liter, which is the same as parts per million. And the blue lines represent the healthy range, roughly 75 to 200. Notice where we are. This is our data. As Jan mentioned earlier, we have 4 give me your pointer. We have 4 places we monitor, and they're color-coded here. And these are the dates and times. Notice the pH, our pH stays right around 8, just a little bit on the high side, but still well within tolerable limits. The alkalinity jumps around a lot. Has some peaks in May. Some of this information correlates nicely with other things that are happening. Some of it doesn't correlate with anything. Some of it may be due to sampling error even. Now, Harrisburg does these tests about once every year. We send in basically a placebo to Harrisburg to sort of check and see if their figures agree with ours. And we're usually pretty close. This is dissolved oxygen. That's very important. Get down below 5 milligrams per liter, aquatic life doesn't survive. You get up too high, it's not good either. Actually, the maximum amount of oxygen that you can dissolve in distilled water near 0 degrees is 18 milligrams. So you may wonder why we have figures of 20. Well, I mentioned before that we titrate this. It's the end product of the titration process, and you're dripping it in with an eyedropper. If you hold the eyedropper a little bit off center, the drops are smaller, so you count more drops, so you can get high value. You have to be very careful to hold the eyedropper straight up and down. That's hard to do when it's freezing out there and the wind's blowing at 30 miles an hour sometimes. Again, down below 5 is bad news for fish.
Question.
Sure.
I presume the reason why you are checking it in 4 different places is to see what happens as it goes along. You haven't made any comparison between what these have. Did you address that?
Sure. First of all, we do it at 4 different places, but it's done at, we only have capacity for doing basically 1 at a time. So they're done it on 4 different weekends typically. So the data is based upon 4 weeks apart. So it wouldn't make an awful lot of sense to try and correlate it. Ideally, everybody go down there. You drop your stuff in, and do it simultaneously. You might be able to get some correlation that way. You would assume that putting stuff in upstream would show up downstream, but we haven't done that. Specific conductivity, we do that in the field. We have a small handheld instrument, and we'll see how that works when we go outside. It's first calibrated against a known solution, and then put in immersed in a sample, and we get a measurement. The healthy values are under 800. We're a little bit on the high side on most of our readings. You see some peaks here. Remember, we talked about what contributes to conductivity, and one of them is the presence of inorganic ions like calcium and chloride, particularly calcium, which is bivalent. And that, not 100% sure since we don't do an analysis on an ion-specific basis, but you're probably looking at runoff from the roads in terms of the salt that's put on the roads. And we tend to get a high correlation with that, and that's kind of interesting too. Now, total suspended solids. Jan put a note on the bottom here, and I've read this elsewhere, that if this thing gets up too high, your macroinvertebrate population gets decreased tremendously. A lot of things happen with high suspended solids. First of all, this is really cloudiness. Water gets too cloudy, the fish can't find their food and can't find each other. It blocks out sunlight for production of oxygen by photosynthesis, and it also tends to raise the temperature of the water because of what's known as the albedo of the water. See if I've left anything out on that. A couple of other things. In terms of the water life, it clogs the gills of the fish. And another thing it does, if you get too much silt precipitating out, falling out, it can cover the bottom. What that does, it smothers the bottom life, which the fish feed on. And so high turbidity is not to be desired. Not an awful lot you can do about it, except here what's been done here in Upper St. Clair is to cut down the silting from the banks. When you've got when the banks are very steep and the water's running by them, it tends to grab the silt and undercuts the banks. You've seen these gabions down here. They work for a while, but the present best management practice seems to be working with rock jetties that go out in the middle. Last week Tom talked about the J hooks and the straight rocks across. What this does is tends to keep the stream flowing down the middle and keep it away from the bank, so it reduces the amount of siltation, which lowers this. It'll be interesting to see over time if these start to come down.
The two high points are from Claire's Kennel, am I reading that correctly?
Yes.
And two different times,
Yes.
both January and July,
Yes.
not weather.
Yes. I don't know what that.
In fact, all your data outliers appear to be at the kennel location. Is there any correlation?
Maybe that's.
Can I address that? Yeah, Ruth Ann just told us 2 weeks ago that the pipe that exits from the bottom of the high school lot is all of the stormwater from Route 19 starting up at South.
You dump a lot of silt in here, and as it moves downstream, it tends to settle out. It doesn't explain why your specific conductivity wouldn't be higher downstream than upstream, but there are a lot of unexplained things here that we're trying to explain. It would be nice, for example, to correlate. We make comments on the sheets we send to Harrisburg, but it doesn't get put into the database as to how much rainfall in terms of comment. It rained heavily today, it rained heavily last night. It'd be nice to maybe try and tie that in maybe more quantitatively at some point in the future. Nutrients, ammonia and ammonium ion. NH3 is really anathema to aquatic life. If you get down to around get above 0.05 milligrams per liter, fish just don't survive. And we do a total nitrogen check, as we'll see later. We don't break it out by NH3 and NH4. If you take the stoichiometric relation between total nitrogen and you know the temperature and the equilibrium constant, you can compute the actual amount of NH3 that doesn't get broken out. But I think it's reasonably low here because we do have some fish in the water. And if NH3 were above 0.05, you wouldn't see any fish at all.
Does that mostly come, obviously some of it comes from fertilizers, I assume, especially.
Here we have nitrate and nitrite broken down by where the source was. For nitrite, desirable to have that under 5. One of the reasons is that bacteria take nitrite and oxidize it to nitrate, and that pulls oxygen out of the water, which reduces the dissolved oxygen, which we know is not good. A desirable nitrate is value is less than 90 milligrams per liter. Also, if nitrite gets too high, we haven't observed that, but if nitrite values get very high, most animals have a what's called a respiratory pigment. Respiratory pigment in humans is iron in the hemoglobin. Nitrite converts regular hemoglobin to something that's called methemoglobin, and that interferes with the carrying of oxygen from the lungs to the cells. So that's another undesirable feature. Particularly in babies' water, in places that's high in nitrite, you actually see blue babies. Now the nutrients, one of the nutrients is phosphorus. Not an awful lot is known about phosphorus. We looked in a number of places to get some information on that. It's definitely needed for growth, obviously. The amount needed for growth is, I haven't seen any standards for that except for drinking water, and the figure that's typically used for drinking water is less than 0.025 milligrams per liter for water in reservoirs, and for water that's not flowing into reservoirs, the limiting value, the suggested limiting value is 0.1 milligram per liter. Iron and manganese. This is done in the laboratory in Harrisburg. We are considering where we are. We have a very low iron. We've observed a very low iron figure in our readings. Manganese is important to life. There's a enzyme in the cell called acetyl-CoA, and it requires manganese for its activation. Desirable figure is less than 1,000. Get manganese up too high, you can taste it in the water, and it starts staining. It'll stain your laundry. And same thing with iron. So it's desirable to have those as low as possible. Our figures here show that we're in pretty good shape in that department. Now, why do you measure discharge? Well, if you measure the concentration of something like iron, and we find out it's 5 milligrams per liter in one sample, in one stream, 1 milligram in another stream, and if these two tributaries run into another stream, which tributary dumps more iron? Well, you can't tell without knowing the discharge. You have to know the discharge and the concentration to determine the total amount that's dumped into the stream. And we measure this as accurately as we can. We had expensive flow meters. We could get a more accurate value. Flow meters are expensive, and they're hard to use in small streams that aren't very deep. So the way we're doing it with a fairly accurate measure of the cross-section and an accurate measurement of the rate at which ping pong balls flow, we get a pretty good idea of what the discharge rate is. And Jan?
Biologists have studied these macroinvertebrates, and they've determined that some of them are more sensitive to water pollution than others. The macroinvertebrates we net, then we categorize. They're either sensitive to pollution, somewhat sensitive to pollution, or tolerant of pollution. You apply a formula to the survey results. So you use the number of macroinvertebrates you netted and the category that they fall into, be that sensitive, somewhat sensitive, or tolerant. You feed this into a calculation, and that calculation yields a water quality score. Now, I want to say quite clearly, the data you're seeing here is based only on one execution of kick netting. That's all our teams have done so far. We went out for the first time last fall. So this is not a deep, broad well of data by any means. And we will get better and smarter, and we'll learn more about it as we go. So I just want to qualify and say quite clearly that we're looking only at one data point here. But according to the macroinvertebrate, our water isn't isn't the most comfortable place to be, I guess, because in 2 of the 4 places, the number and type of macroinvertebrate that we netted and counted indicated that the water quality was poor, and in 2 of the 4, the water quality fair. At the same time that we execute our kick netting, we do something called a habitat assessment survey. This habitat assessment survey yields a subjective, and it is subjective because it's a series of questions, and for each question you give the answer to the question in the form of a ranking from 0 to 10, where I believe 0 is poor and 10 is excellent. So it is subjective. But it does come out with a number at the end, a qualitative measure. And the things that you're trying to measure with this survey are, you're looking at the natural habitat availability within the stream channel, you're looking at the stream channel conditions, and you're looking at the stream bank and riparian buffer conditions. Does everybody know what a riparian buffer is? A riparian buffer is the vegetated buffer beside the stream. So that would be the bushes, the grass, the trees that border the stream. And a riparian buffer is a great health benefit to the stream because it works basically as a huge filter. As runoff comes through the vegetation, that vegetation will absorb nutrients and contaminants. It shades the stream, it helps keep the temperature of the stream down. The roots provide stability to the stream bank and help stop erosion. So a riparian buffer is a very healthy thing for a stream, and the wider and more dense it is, the better. So we did our habitat assessment, again, a one-time deal. We're only looking at 1 data point. And we found that Drake Loop the habitat assessment was not very positive there. And I don't know if you guys can picture Drake Loop, but the Drake Loop site is probably our most heavily man-modified, might be the right words. One side is constrained by a 3-story cement wall. The opposing bank is completely gabion baskets. So that stream has been heavily channelized to pass right beneath Fort Couch Road. And then after it passes beneath Fort Couch Road, it does a turn, and the habitat improves a little, but it is still definitely our most heavily man-modified site. So out of the maximum score, if you got a perfect score, would be 200. So you can see the 4 sites that we're monitoring at range from something that's not real good. McLaughlin Run scored just above 50. My guess is that's about 60. But at Claire's Kennels, where we'll be today, if you look around there, you'll see that the riparian buffer on the far side of that stream is kind of nicely intact. Now it's naturally steep, but it's still naturally vegetated, heavily vegetated. So there are some benefits at that site, and it scored the highest at probably 155. Now, an interesting comparison. Where did we find the creek critters and where didn't we find the creek critters? Because remember, this water quality score is basically based on the number of creek critters we found and the kind of creek critters we found. Where our habitat assessment survey didn't give the stream a very nice habitat score, we didn't find a lot of things living in it. There appears to be a correlation there between those 2. Again, we'll follow that as we collect more data over time. So let me give you a brief summary. Now, this isn't, there's more that could be done with this data. There's many more things we hope to find out, and the data will tell us more and more over time. But looking at the data we have available to date, I'd have to say that from the point of view of chemical monitoring, from outside looking in, the specific conductivity levels are consistently above acceptable values. That's a problem. One of the probable causes is we're pretty sure one of the probable causes is road salt. But it appears that there's something else going on there. There's some other cause, because you don't see those spikes only in the winter. Although you see our highest spikes in the winter months, you see elevated levels of specific conductivity in these waters pretty much all year long, according to our monitoring. And we're going to try and look into that. From the point of view of the macroinvertebrates, or from the inside looking out, apparently McLaughlin Run watershed is not the worst, but certainly not the best neighborhood in town. The probable causes are that stream habit modification and combined with our existing pollution levels. Now I want to go back for just a minute to the big picture. This is Chartiers Creek watershed. The watershed that we just talked about is this small McLaughlin Run watershed. All of the data that we've collected is on these two streams that you're seeing here. All of these streams contribute their contaminant load to Chartiers Creek. It's a cumulative effect. You can see there's a lot of streams in this watershed. Now, some of those streams, the water quality is probably better than that of McLaughlin Run. Some of those streams, the water quality is probably worse than that of McLaughlin Run. But all together, as they empty into Chartiers Creek, they have a cumulative effect. And the quality of the water in Chartiers Creek is linked inextricably to the quality of water in all of these tributaries to it. And then as Chartiers Creek flows downstream and gets its cumulative load, be that good or be that bad, from the streams feeding it, and it empties into the Ohio River. A good deal of Pennsylvania gets its drinking water from surface water sources. My guess is somebody's withdrawing their drinking water from the Ohio River. And so now we're going to refer to the theme, the watershed in your wallet. Where do the dollars and cents come in? This is the minimum, maximum, and average values for some of the parameters we monitored for in McLaughlin Run Creek, and this is the PA Department of Environmental Protection drinking water maximum contaminant levels. So where I've marked our monitoring results in red, our monitoring results are show significantly higher concentrations in the McLaughlin Run stream, or excuse me, in either the McLaughlin Run or the Grazier's Run stream, than is acceptable in drinking water. The bottom line, in many cases, what goes in must come out. This costs dollars. And I thank you very much. That's the end of our presentation.
Have anything in it, and then 2 more samples that we will put in drops. Thank you very much for getting that over.
Stream, 3 bottles, 2 small and 1 large. The large bottle will be used for a number of chemical analysis at the lab in the Harrisburg lab at DEP. The 2 small bottles, one will be used for metals. The second will be analyzed for NP, nitrogen and phosphorus. The metals and the nitrogen and phosphorus bottles are acid fixed. We add a dropper of acid to each to lower the pH inside the bottle significantly, and this stops chemical reactions from depleting either the metals or the nitrogen or the phosphorus in the bottle. Because if you didn't do this, you would send it to the lab. There's processes that can take place at neutral pHs that would deplete those things, and you wouldn't see them in the analysis. We spill these acids, and we don't want to get them on our skin or in our eyes. They are acids. They'll burn your skin. You definitely don't want to get them in your eyes. These guys both... one of them is nitric acid, and one of them is acid, HNO and H2SO4. We're icing down those samples, and chilling them is for the similar reason to acid fixing them. Will be slowed down by being chilled. All of that stuff happens more rapidly at elevated temperatures, so you're stopping changes or you're slowing down any changes that might take place to the samples between here and the lab. It would give you a correlation between sites, but in fact still they would be snapshots. And really the plan with the snapshots is to look at the snapshots over time.
But
to
then
get
you would see that we did down there was doing a whole lot of good, whereas the stuff coming off of
This is our Hanna water check meter, and it's capable of reading both specific conductivity and pH in the stream. But one of the first things you have to do to the instrument is calibrate it. It's very important to calibrate an instrument. How are your hands, Bob?
Okay.
Cold.
Pretty clean.
The little screwdriver that Bob has in his hand to adjust the instrument just in small degrees to ensure that it registers exactly 7.0 while it's in that solution.
No,
Go ahead.
go ahead. He's put in 1 and 2. Dissolved oxygen 2. What are these items that we're putting into
Do
this
you know,
water?
I have read that information, but I didn't retain it. FIFO.
You haven't calibrated something?
Yes.
Okay.
I am. Good, thank you. All right, then after that comes,
One, it requires 3 or 4 steps. We're trying to do that first.
take forever, but it will eventually settle.
Oh, Bob has now taken the water check meter down into the stream, and he's immersed it into the flowing stream, and he'll get us a pH reading for the stream. Remember on our chart in there, we were consistently right around 8. So, again, we're right around 8. The same process, we're going to calibrate the water check meter for specific conductivity with a solution of known value. Bob, I'm sorry, Bob. Calibrated to a solution of known specific conductivity, and now Bob's going to take a reading in the stream.
These standards all have different, I do, huh?
Yeah, the meter's reading over range.
Read 0 to 1990 microsiemen per centimeter specific conductivity. Generally, what we've found when we get the reading that Bob got, which is the meter refuses to give you a number, then the specific conductivity in the stream is higher than 1,990. And I was explaining that we get specific conductivity results in 2 ways. The large bottle that we send to the lab, they also execute specific conductivity analysis. So we will get a number back from the laboratory. And consistently, when we get that funny reading on the meter in the stream, the lab sends us back a number that's bigger than the limit. Now, this is admittedly a rough estimate of discharge or flow, but it is a reasonable estimate. What Larry and Bob are going to do is measure from water's edge to water's edge 5 times across the stream.
The idea is to get an average cross-section value.
Right.
Which can be used to determine the volume you're talking about when you measure the time it takes for the ping pong balls to flow. And from that you get a time rate discharge figure. In
Absolutely.
cubic meters per second or cubic feet per minute. Or
Does that make sense, Larry? Good.
7.95.
we measure. Flow?
Yeah.
It's not very aesthetic.
Good place for that, right?
Yeah, right here.
Yeah, you put boards across there, put a B in there.
Right.
Halfway down, and we're going to shake it and let it settle again.
This ensures you get a nice precipitate.
Okay? High five.
There's a lot of chloride.
It's partly coming up with the right equipment and you know, this funny business about these boots, but...
Spin around the circle.
While he takes pictures.
I'll put some in.
Oh. Our guy generally does the monitoring on Monday. They measure this one.
Okay. They're, whoops, I have to hold down there to this big tree here. I'd actually like to pick a place that gives me...
Tell what he's doing.
So Bob is using our ever faithful yardstick, and in fact this yardstick is used in a number of our streamside processes. Currently he's taking the depth, he's measuring the depth of the water in centimeters 5 times across the width of the stream. We'll average these 5 values to get an average depth.
Measuring in centimeters.
Did I say that?
There's a spare.
Wow!
That's something fancy.
Take another one in case you drop.
No, that's what the idea was.
They do. One of the impressive things that Dan's done is to put that whole kit together. Yeah. With all of the equipment. I mean, it really is.
And they're off.
You might indicate that sometimes the wind carries, it gets caught in an eddy.
Now the
Okay, I am now. Sorry.
Now, Larry and John have placed themselves exactly 10 meters apart in the stream. The objective here is to drop the tennis ball and allow the tennis ball to be carried downstream by the current, and the amount of time it takes the tennis ball to go 10 meters should give you an estimate of the velocity of flow in the creek. Unfortunately, today there's a little bit of wind and the ping pong balls are going upstream, which does not give us a good estimate of downstream flow in any way, shape, or form. Now, we're going to try again in another part of the stream to see if we have a bit stronger current in that part of the stream and or if we can get a break from the windy conditions.
It looks like it's moving.
And she's off.
Oh, wait, you increase the data because they won't move. We should normalize the data for further put in. In other words, use the depths at the point where the stream is moving, not when don't average in the depth where the stream is not moving.
Boy, okay.
We haven't been doing that. We might look into checking with DER to see if that's acceptable.
Okay.
Jan, we have some people that are really very interested in the kick netting in this group.
Good.
We have to be sure and give them the dates and the times, and
Excellent.
places. I think we have everybody's email address here.
I don't
She's a
know.
member of
You know,
CLA.
we should have brought a sign-in sheet.
Yeah.
We didn't.
Well,
Silly us. Who's interested?
Yeah. YMO may be interested.
Well, I'm sure I know Annette has it, and I think I have it too.
She's standing to Lois's
Larry.
right. Foster's right. That's why I can't see her.
Oh, Pedersen.
What's her name?
Pedersen?
Anyway.
All right. I'll
Carrie Pedersen. Peterson. Peterson. No, oh.
Cheer it on.
Yay! Now, using the average width of the stream that we've calculated, using the average depth of the stream we've calculated, and using a 10-meter length, we can build an imaginary box of water that tells us the volume of water we're dealing with, and then the amount of time the ping pong ball took to go 2 meters, 2 minutes, tells us how quickly that water is flowing. So that can be translated into a cubic centimeters of water per second flow, or volume of discharge.
Okay?
That was a good one.
We have one more.
Ripping right along.
Doesn't want to go
I
in.
see that. It does not want to at all.
There we
There we
go.
go.
Finally. Okay, and we shake it again.
Is that dark?
It is. Well, there is a bottle of water that we filled down in the stream, and we added 2 chemicals to it and allowed the chemical reaction that they begin to take place, and it caused a good deal of precipitate to settle to the bottom. Now, Annette has added a 3rd chemical to the bottle. We've shaken that up, And now we're going to do what Bob referred to as titrate what's in here, and that'll tell us how much oxygen is in, dissolved oxygen is in the water. Here, can I have a volunteer? Bob, you want to talk or help?
Sure.
Either one?
You hold the microphone.
Okay.
We're going to fill up a graduated,
Hold this underneath so you don't spill anything on the ground.
small graduated cylinder of known volume.
Good.
That puts a known volume of this material in there. It'll come out.
Oh, yeah?
It's hard to do, huh? There you go.
Okay. If you want to hold that, we have to rinse that out. Okay. And
Let's
then
work over top of something again so we don't spill anything.
we're going to put in a full fat drop. Okay, and we're going to count. 1, and we're going to shake. 2.
Did you
and
show
shake.
Preston the color?
3, shake. Can you see how it's getting lighter? 4, 5, 6,
Typically takes about 13.
7,
Mm-hmm.
8, 9. See how it's getting clear? 10. 11. 12.
Almost.
Not quite.
13. I'm going to put one more in.
One more?
I think it's not
Put one more in and we'll decide.
13. 14.
Yeah.
Yeah.
Yeah. So what
Okay.
does that? What does the 14 drops tell us, Annette?
It's the amount of dissolved
Milligrams per liter.
milligrams per liter
Mm-hmm.
dissolved oxygen. 14.
Mm-hmm. You've seen basically all the processes we go through monthly to collect the field parameter data and to make available to the laboratory in Harrisburg the samples that they need to do the laboratory analysis. So the work we've done here streamside and the results we get back from the Harrisburg lab will continue to provide us with the valuable data of the same kind as you saw today in the classroom.